Good day, yo. So, tomorrow, we're testing. Tomorrow, it's only a day away. That's right, Science EOG is tomorrow. So, I'm going to give you a quick and down dirty review of the full year. And if you can keep up, here's some stuff you need to know to go ahead and kill this EOG tomorrow. We're going to start off with your chemistry review, talking about what's a pure substance. What you gotta know is that a pure substance is made of one type. It's all the same. If it's all pure, we call the simplest things that are pure on our planet elements. We know that if you combine two elements, if there are two or more and they're chemically combined, okay, they form compounds. Now, if you're looking at a compound, here's a question some of you got mixed up on, is that they do combine in what we call fixed ratios. Keeping in mind that elements want to combine to form this perfect number of 8. So if you're looking at your periodic table, once again, family 1 best bonds with family number 7 instead of a 1-to-1 ratio because they both satisfy what each other's needs. So they do combine in specific ratios. I said specific, not the same. So keep that in mind. So this is a picture of an element. So everything's the same. Here's a compound, two or more different things, and they join them together so they would be combination. So if something is not pure, we're going to call it a mixture. The key word for mixture is that they are physically combined, therefore they can be physically separated. These two things go together. So there are two types of mixtures, homogeneous and heterogeneous. Homogeneous means that it's so much the same. Okay, it is so much the same that you can't tell it apart. So let me see if I can make, there we go. So heterogeneous therefore means it is so different you can see the different parts in it. Another key thing to remember that the word solution means liquid mixture. Once again, a solution means a liquid mixture, and all liquid mixtures are homogeneous by definition. So this would be a homogeneous mixture of compounds. So once again, there are different compounds, but they're together, so it's a mixture. And here's another one. So keep that in mind when you're looking at that. Examples of this would be homogeneous would be anything water, air, steel, salt water. You can't tell them apart, so there'd be homogeneous. Chex Mix, tar solid, granite. These would all be heterogeneous because you can see the differences. Okay, that takes us to the periodic table. And if you're looking at your periodic table that you will have tomorrow, the number on the top is your atomic number. This equals the number of protons and or electrons. Keeping in mind that your protons, which are positively charged, and your electrons, which are negatively charged, are always the same number. The bottom number to the bottom is your atomic mass number, and that's a product of your protons and your electrons. Okay, your symbol name. So this is information, if I were you, I would label on our first part of my periodic table. So as you're going through it, you can always remember that. Okay, things to remember that if you're going down a column, these are called families. Okay, and that family means they're similar. Another word for family would be groups. Okay, or columns. So they mean the same thing. That means that they act the same way or they're similar. The key word, they're being similar. Okay, if you're going across you're going across a period or a row. That's the word they like to use here together. And these are going left to right. Key thing to remember is that they have nothing in common with each other. Okay, they just happen to be side by side. Now, on your periodic table, there are three main categories. Here we have all of these guys are metals. Here we have our non-metals called gases. In the middle here we have a liquids or metalloids. So metals, metalloids, and your gases. On your periodic table on your test tomorrow, I would go ahead and create the numbers that make sense to you. So 1, 2, skip over the ocean. 3, 4, 5, 6, 7, 8. There are 8 functional groups for 8th grade science. If you notice down here, these numbers have the letter B next to it. So these are B groups. Their rules are a little bit different. We looked at the rule of 8, saying that how families form or elements combine to form compounds in specific ratios. And we said that that ratio is about fulfilling each other's needs. So family 1 has 1 electron in the outside shell that they want to get rid of. It just so happens family 7, called your halogen gases, have 7. 1 plus 7 is 8. Therefore, family 2, your alkaline earth metals, bond really well with family number 6, because 2 plus 6 gives you 8. So 2 gives up 2 electrons, family 6 take them on, and now they all fulfill each other's need. So so as you're moving left to right across your period, your reactivity goes down. So everything that's highly reactive is on the left side, this side over here. Everything that's non-reactive or less reactive would be on the right side, culminating with family 8, your noble gases, which are unreactive because they have all 8 valence electrons, and you don't have anything they need. So how are they separated? Well, they're separated by what metals are. So metals they're shiny, they're malleable, ductile, and able to conduct heat and electricity. So if on your EOG they ask you the question about any one of these things, they're really giving you the answer to say, hey, it must be a metal. Okay, and here are the meanings. You can pause it and look at these and read for yourself, and look at how they go. So here we got some common compounds that you should probably recognize by sight. Water, which is H2O, glucose, C6H12O6, oxygen, hydrochloric acid, HCl, carbon dioxide, table salt, NaCl. Keeping in mind that when we're looking at compounds, that every capital letter means a separate element. So water is a combination of hydrogen plus oxygen. 2 hydrogen, which is designated by the subscript here. So for every 2 hydrogen, you have 1 oxygen. Keep in mind, oxygen is in family number 6. So it needs 2 electrons. Hydrogen is in family number 1, or inside the first column. Therefore, it only has 1 electron to give up. So it takes 2 hydrogen to make 1 oxygen work. So the ratio is 2 to 1. So compounds combine in specific ratios, even though the ratios can change based upon which compounds they are. Alright, so that takes us to the other part of chemistry, talking about physical and chemical changes. Keyword to note here is that the physical change is reversible. It may look different, smell different, but it's not different. A chemical change is something where, keyword here, you're going to make a new product. Something new is being made. And that new thing can be designated by rusting, burning, reacting with acid. Water is your trap answer here. Water can go through whether it's melting, freezing, or boiling, but still be water because you're not making anything new. So water is one of the few things that can have all this stuff happen to it and still just be water. So the last part of chemistry talked about the law of conservation of mass, which says that in a chemical reaction, whatever you start with must be what you end with. The word for start is really called reactants, and the word for ending is called your product. And so if matter cannot be created out of thin air, whatever you start with must be what you end with. When you're looking at this, you're going to look at your equation and say, okay, how much of this do I have? So the 2 here, which we said was your subscript, means that you have 2 hydrogen. This 2 here behind the oxygen means you have 2 oxygen. So this is your starting ingredients. If this is what you're starting with, they may look different on the back end, but the numbers should be the same if that law is true. Now this big 2 over here is called a coefficient. A coefficient multiplies a number. So 2 times 2. So we're saying 2 times this 2 here equals 4. Now right here is where the trap is. Even though you don't see a number, the 1 is understood in chemistry. So we're going to say 2 times the 1 that's invisible, but we know it's there, means that we have 2. So because these numbers don't match up, we will say this equation is balanced. When you're looking at this on your EOG, they're not going to ask you to balance it. They're going to ask you to look at the equation and say, hey, if I were to break all of my elements down individually, is the number of hydrogen equal to the number of hydrogen on the product side? If they're not, it's not balanced. If they are, and everything else equal, then it is balanced. And so that completes the law of conservation of mass. It fulfills the law that says whatever I'm starting off at my beginning, or my reactants, is what I'm ending with, also known as my product. And if they're not, then it's not balanced. So because this can be a tricky one, let's go through. So here we have a chemical reaction causing a sealed tube. So a sealed tube is really your answer. it's telling you that nothing is getting out. So if that reaction is in a sealed area, then the law is absolute. So whatever you start with, you must end with. So the product, they're saying, of the end result is 24 grams. If I'm ending with 24, how much must I begin with? Well, I must begin with 24 because matter cannot be created or destroyed. So the answer for this one would be A. With this one here, which says the same one, if you start with 10 times more, how much should you end with? Well, I should end with 10 times more. So remember, it says starts, which means my reactant. So if my ingredients to this recipe is 10 times more ingredients, well, whatever I make should be 10 times more. So don't let these questions really mess you up. They're fairly easy. So let's do one more before we move on. What is the total number of oxygen atoms in the reactant side of the equation below? So we can call out our oxygen. So 1 plus 1 is 2. So we have 2 of these guys. And then we have 3 here. So 2 plus 3 is 5. Now we know they're on the reactant side because they're in front of the arrow. So don't get really messed up on it. I know it's been a while since we've done that, but keep in mind the law says whatever you start with, you should end with. So if you can apply that law, this should be fairly simple. So now we to fossils. Solid. Yeah. Solid as a rock. So fossils really are rocks. Now there's some important fossils to know. The most important one you got to know is the index fossil. And the index fossil must have lived for a short period of time and got to be fairly common. The next thing, remember that index fossil tell you the relative age. Keyword there being relative age of rock layers. So not an exact age. So the index, which means pointing, tells you, hey, if I find this index fossil here and it's X amount of years old, the fossils underneath it must be older. The fossils above it must be younger. The fossils found in the same rock layer will be the same age. So index fossils tell you the relative age of stuff around them. The next thing to keep up is that ice core. So fossils tell you about the living things, the plants, the organisms, the animals. Ice cores, however, tell you about the atmospheric changes. And so they tell you about how the weather was, how the climate was because of the gas bubbles that are trapped in there. So keep that in mind. Next, remember that pretty much all of your fossils, or all of them really are sedimentary rock, because igneous rock comes from a magma, and we know that anything in magma will burn up and get destroyed. So here's a good question about index fossils. Why are index fossils good clues? Well, so when we find index fossils, I'm going to look right away for something to do with age. Oh, they only for a specific period of time. So you're going to match your vocabulary up with some of these. The next one was the law of superposition, which says that if you took a bunch of rock layers that were left alone, the oldest ones would be at the bottom and the youngest ones at the top. The one that breaks the rule here is called a intrusion. And we said an intrusion is younger. So this guy is breaking through. Is younger than any rock layer goes through. So, but it must go all the way through. So the oldest one would be Z, then Y, then X, then your intrusion, then layer W. So that's how we can look at that. If we're looking at fossils once again, we're looking at the change over time. This gets a little bit of evolution, which I'll cover in a second. So fossils also continue how animals change because fossils are the evidence of living things. So if I find the fossils of different horses in a rock layer at different depths, from oldest to youngest, I can look at how the horse may have changed over time. So fossils really give you a good evidence, or the best evidence of evolution on our planet. Here's another common question on fossils. Say, which can scientists infer when they find marine fossils? Keep in mind, marine means ocean. So if I find a marine animal on top of the mountain, well, the fish can't swim there. What it means is that at the point in time when this fossil was being formed, that area must have been underwater. So use your hints. So here would be, the mountains were created. So at that point in time, there were no mountains, but when the mountains were made, they were underwater and it got lifted up. So be careful here. A lot of these things have some really good hints in them. Find your keyword. So keyword is climate. If I see climate, well, gotta be ice cores because ice cores have with the climate. All right, let's move on. So we looked at relative dating, which we use index fossils and